Good morning, class. We are looking at practice test number 4, covering module 4, chapters 8 and 9. Here's chapter 9, inferences from 2 samples. Among 843 smoking employees of hospitals with the smoking ban, 56 quit smoking 1 year after the ban. Among 703 smoking employees from workplaces without the smoking ban, 27 quit smoking a year after the ban. Part A, is there a significant difference between the two proportions? Use a 0.01 significance level. Well, first and foremost, let us write what is given, everybody. We are dealing with the binomial distributions because the outcomes are true, either quit smoking or not. N1 is 843, 56 quit, and N2 is 703, 27 quit. Alpha is 0.01. The very first step is to write H0 and H1. As you recall, when we do the test of hypothesis, we cut it into 4 pieces. Step 1, we need H0 and H1, but let me just remind you of some of the formulas that is needed here. For example, P bar is x1 plus x2 over n1 plus n2. Z is p1 hat minus p2 hat over the square root of p bar q bar over n1 plus p bar q bar over n2. It's similar to one sample, but it's a little bit more complicated. Therefore, let us calculate everything that we need first. And for example, we need a p1 hat, which is x1 over n1. We need p2 hat, which is x2 over n2. We need p bar, which is the sum of x1 and x2 over the sum of n1 and n2, this formula. We need q bar, and of course, q bar must be 1 minus p bar. Q bar must be 1 minus p bar. All right, we are ready to do the business. Step 1, H0, P1 minus P2 equals 0. First and foremost, remember, when we write H0 and H1, we just have to write population parameters. And it is always the equality that belongs to H sub 0. For H sub 1, either P1 minus P2 is larger than 0, less than 0, or it's not equal to 0. So let's read the question. Is there a significant difference? That means not equal. And that makes it a two-tail test. And since we are working on that, we're going to set that as a claim. By any chance, if you wrote instead of P1 minus P2 equal to 0, if you wrote P1 equals P2, that's fine. Then this goes to P1 is not equal to P2. So just be consistent. Either these two or those two. This makes it two-tailed because of the fact that it's not an equality, and we're going to work on that as a claim. And we are going to move on. So the next step is to calculate the test statistic. Here's the formula, and we've done everything we need here to get to this formula. We are ready to move on with this formula. using this one, P1 hat minus P2 hat. We are looking at this formula. And then the square root of P bar Q bar over N1 and then over N2. Now, thought I put N1 here. Okay, class. Now we do the math. We end up with 2.4319. Critical value comes from the choice of alpha, which is 0.01. Z is plus minus 2.575. Remember, with the binomial distribution, we always go to the Z distribution because it's an approximation by a normal distribution. And so what we have, we are going to draw the graph. We have a negative and positive 2.575 as the critical points, meaning to the left of them we have the critical region or rejection region. In between it's not. This value that we have calculated, the test statistic of 2.4319 is somewhere here, which puts us way into the non-rejection area. In between is a non-rejection area. So therefore, the decision is very simple. Fail to reject H0 or the null hypothesis. All right. So we're going to go back to the very first step. We are not rejecting H0. So in essence, what are we rejecting? H1. So what are we rejecting? The claim. The claim becomes false. Now we just rewrite and we say there is not a significant difference between the two proportions. Because the question was, is there a significant difference between the two proportions? We ended up with H0 being the true statement in essence. So that's that. And let's look at technology. And we are going to use two proportion Z test. And when we do that, we put X sub 1, N sub 1, X sub 2, N sub 2. P sub 1 is not equal to P sub 2. And we calculate. It gives us those information. And take a look. First of all, P1 hat and P2 hat that we calculated. For example, P1 hat is 0.0664, P2 hat. And then we have this value, okay, which is the P bar 0.053. And if you stop here, 6 changes to 7 because next to it is 8. And the P value, here's the P value, everybody. So P1 hat, P2 hat, P bar. This is the P value, which makes it 0.01492, and it continues indefinitely. But if we stop at that, clearly is larger than the choice of alpha, which was 0.01, and we failed to reject the null hypothesis, the same decision. Okay. All right, we're going to continue with the same question. Part B of the same question, we want to construct a 99% confidence interval. So first, let's remind everybody what we had from the previous page. It's a binomial distribution. N1 and X sub 1 are given. N2 and X sub 2 are given. Alpha is given. P1 hat, P2 hat, and P bar and Q bar were all calculated. Okay. And so if you look at the graph class, we want 99% confidence interval. And since alpha is 0.01, and in part A, we had a two-tailed test, then 99% confidence interval corresponds to 1% alpha. Therefore, the same z-value works. So this is 99% with the same z-value. Okay. And so the formula is a P1 hat minus P2 hat minus E and P1 hat minus P2 hat plus E. P1 minus P2 is between the two. Just plug in. And as you notice, basically, we have everything from here. Plug in. And the Z value, just put 2.575. By the way, plus or minus, it doesn't matter. The reason you have a plus or minus because this is the negative, this is the positive. So let's find the value of E by plugging in the value for everything that is given here. Notice I wrote P1 hat is 0.0664, but I put more decimals here. You really don't want to do the rounding until the last step because any intermediate step that you do the rounding, you end up with what's called round off error. So you just simply do this calculation. Calculation may be tedious, but the concept is very simple, class. So you simplify inside the radical and you end up with this number as E, 0.0289. So P1 hat minus P2 hat, we are going to add and subtract this number from it. P1 hat minus P2 hat ends up being 0.028022. We are going to subtract this number from it and add to it. P1 minus P2 is between these two numbers. Negative 0.000878 and positive 0.056922. If you don't put enough decimals, this ends up being 0, which is wrong. Okay, it's a negative value. Make sure you use enough decimals. So what happens is that you are going to go from a negative value to a positive value, which means P1 minus P2 does contain 0. And therefore, with the use of a confidence interval, you get to the same decision. So traditional method, the p-value method, and now the confidence interval. Because the confidence interval limits contain 0, see, this is between negative and positive. There is not a significant difference between the two proportions, fail to reject the null hypothesis. In other words, P1 is equal to P2. If it goes from negative to negative, that's not the case. If it goes from positive to positive, it's not the case. Normally, if it goes from negative to negative, means P1 is less than P2. And if it goes from positive to positive, that means P1 is larger than P2. That's the meaning of it. Now, as far as the technology is concerned, we are going to go with the confidence interval of two proportions. And we're going to input x sub 1, n sub 1, x sub 2, n sub 2. The C level is 0.99 or 99%. When we do the calculation, this is what we end up with. And you notice this is what we want. If you look at this number, it means negative 9 times 10 to the power minus 4. This one, if you look at this one, 0.0569, then this is 5, this is 2. Of course, why is it different? They use a lot more decimals. But I want to make sure you understand this number means negative 9 times 10 to the power of minus 4. And as you know, you just, the decimal is here, you move it 3 places, it becomes a minus 0.30 and then 9. If you notice, if I stop here, I have to change it to 9, becomes identical to this number. So this number, let me write that. This number is equal to minus 0.0009. Okay, it's using scientific notation, everybody. Scientific notation. All right. So as you can see, this is the same as this. Slightly different, slightly. Could somebody read this for us, please?
Company A claims that its yogurt cups contain, on average, fewer calories than that of a competitor. A sample of 50 such yogurt cups of Company A produced an average of 141 calories per cup, with a standard deviation of 5.4 calories. A sample of 40 yogurt cups of a rival Company B produced an average of 144 calories per cup, with a standard deviation of 6.3 calories. If the calories of the yogurt cups for Company A and Company B have different variances, use a 0.01 significance level to test the claim.
Excellent. So let's see what we have. Here's the given NXS for Company A, Company B. So you plug in. So the first company, Company A, let's say it's N sub 1, 50, X sub 1, 141, right? On the average, that's the number of calories. With a standard deviation S sub 1, 5.4, okay. Whereas here is N sub 240, X sub to 144 calories, and S sub to 6.3. So we write the given in this table. It makes life easier so we can refer back to it. This is alpha. There are 4 steps. Starts with step 1. H0 mu1 equals to mu2. H1 mu1 is less than mu2. That is the claim, and that's the left tail test. First of all, less than means left tail test. Secondly, that's the claim from the company. So we use the test statistic x1 bar minus x2 bar over the square root of s1 squared over n1 plus s2 squared over n2. Similar to what we have seen for one sample. Again, this is the formula available to you. And now all we have to do, use this table and plug in. That's why we wrote the table symbolically, so it makes life easier. Let's plug it. By the way, in many texts, they put this minus after that. The minus that I put, because the formula is minus mu sub 1 minus mu sub 2. In other words, the formula that I'm referring to is this. In some texts, they write the numerator. I'm going to write the numerator only as x1 bar minus x2 bar minus mu1 minus mu2. Now, what happens is that mu1 minus mu2 will come from H0. By the way, H0 we wrote mu1 equals mu2. We could write it in the following manner. As long as we are consistent, it's fine. We could write this as mu1 minus mu2 equal to 0. If you go with that, then you should write mu1 minus mu2 less than 0. Okay. Either way is fine, just be consistent. And now when we do the math, we end up with negative 2.3901. If we are using tables and limitation that we have there, the degrees of freedom, critical value comes from the choice of alpha is 0.01. And degrees of freedom is going to be smaller of the two, n1 minus 1, n2 minus 1. And so this is 50 minus 1, this is 40 minus 1. So the answer will be 40 minus 1 or 39. And from the table, we get to negative 2.429 because it's a left tail test. So if we were to draw this, here's a graph. Here's your critical value of negative 2.426. Here's the test statistic that is evaluated. By the way, alpha is 0.01, and that is way into the, as you can see that, way into the non-rejection region. Therefore, fail to reject H0 or don't reject. Normally, they use fail to reject H0. Either way is fine with me, but just stick with the way they want it. If you do not reject H0, what are you rejecting? H1. What are you rejecting? The claim. The claim becomes false. And therefore, you rewrite this. There is not enough evidence to support the claim that company A's yogurt cups contain on average less calories than that of its competitor. Now, of course, when we use the technology, degrees of freedom is actually calculated, so things may be slightly different. But let's move on with this question and go to part B, and the same question, we want to calculate the p-value. What I want to show you, I'm going to show you by hand using the table, and at the same time the technology and what happens to that. Again, we're going to write the information from the previous page, this table, this one, and now I am showing you the t-table here. So when we want to use the p-value, here's the test statistic. So we want to compare this area. I mean, you can tell clearly that just from the graph, it's way larger than alpha, and you get to the same decision, which is fail to reject H0. But the methodology is area to the left of test statistic, which has t-value equals negative 2.3901. And if you want to go with the table, degrees of freedom was 40 minus 1 or 39. And you can, the values that are given are positive. You're looking for this value in the table and you don't find it. So look at the positive 2.3901, which we don't have. But I hope you see that it's between these two numbers. Between these two numbers. This number is between these two. And area in two tails is between these two, but we want area in one tail because it was a left tail test. So this is the area we want, and the area is between these two. So the p-value, we don't have it. But it's between these two numbers. Clearly larger than 0.01, and that gives us the same decision. Again, same decision, failed to reject the null hypothesis. Decision is in agreement with the previous part. Now, this is using the table, not using the technology and so forth, and the limitation we have. Let's see what happens when we use the technology. So two sample t-test, and we put in x1 bar, s, n1, x2, sx2, n sub 2, and we are going to go with less than. It says polled, and we are not going to poll because we do that when we assume equal variances. That's not what we did. Okay, we assumed different variances. And so when you do the math, notice what it does. Calculated results are different since degrees of freedom has a different value. First, I want you to look at the degrees of freedom. Okay, the degrees of freedom has this formula: a plus b quantity squared over a squared over n minus 1 plus b squared over n2 minus 1, where a is s1 squared over n1 and b is s2 squared over n2. This is the precise value as to how you calculate the degrees of freedom. And degrees of freedom, so take a look, degrees of freedom is not 39. And the p-value, 0.009642, it's very close. If you stop here, that this becomes 1 and becomes identical to that. But the fact of the matter is the p-value is less than that. Even if it's equal to that, you reject H0. So we do get a different result from the calculator. And again, as long as you show your work, even if there's a discrepancy, I'll be more than happy to look at your exam, adjust it. But understand why it's different, because the degree of difference is completely different than what we assume. This is the assumption in most texts when they have to rely on just the limited resources available versus technology, which can obviously do a better job. We want to continue with that, and we want to get a 98% confidence interval. Bear in mind that alpha was a 0.01, and it was a one-tail test. It doesn't matter if it's left-tail test or right-tail test. It's one-tail test. So 0.01 times 2 is 0.02. It corresponds to 98% confidence interval. So 98% confidence interval corresponds to alpha of 0.02 for a two-tail test, alpha of 0.01 for one-tail test. Left tail or right tail makes no difference. So you can think of another tail here, 0.01. So in the middle, so 4, see what, if you think about this, this is the 98% confidence interval. This would be another tail if you're dealing with a confidence interval. And we're going to use x1 bar minus x2 bar plus minus. Now, what I want to show you is that a lot of calculations have already been done for E, and we're going to plug in. So I'm going to remind you of this formula. In the numerator, we have x1 bar minus x2 bar. So this is this part. In the denominator, we have this one. So what is E equal to? Here's the formula for E. T alpha over 2 squared of S1 squared over N1 plus S2 squared over N2. So this part is identical to this part, isn't it? Therefore, I don't have to do the calculation. For this one, I pick this number. For this one, I pick the T. Again, positive value. So notice you pick these numbers. Okay, those are the T. So in other words, everything that we have done before in previous page, we keep it. And this number, we pick it up from the denominator of the test statistic. My point being, you really don't have to go through the process again. Just plug in, evaluate. The product is 3.04504. And so remember, the numerator is -3. You are going to subtract this number from it, and you're going to add to it, because it's x1 bar minus x2 bar, which is -3. Add and subtract this number. So we get -6.04504 and positive 0.04504. So what it means is we are going from negative to positive. It includes 0. Because the confidence interval limits contain 0, there is not a significant difference between the two means. Fail to reject the null hypothesis. So in other words, we had decided not to reject H0 in the first place. And whether you go with the traditional method, the p-value, or the confidence interval, you should come up with the same answer. The only thing that might have a difference is, again, when we use a technology. So if we use the technology, okay, two sample t interval, and we plug in x1 bar, s1 bar, n1, x2 bar, s2 bar, n2, and 98%, and is it pulled? No. When we do the math, this is what we get. Minus 5.982 to minus 0.018. Okay. So obviously it's different than what we have. But why is it different? Because of the degrees of freedom. Since both of them are negative, you reject the null hypothesis. So again, I want you to see that. So the calculated results are different since degrees of freedom has a different value. Because the confidence interval limits are both negative and do not contain zero, there's a significant difference between the two reject and null hypothesis. Two different answers based on technology. Go ahead, Amanda. You have a question?
Yeah. One, can you hear me okay?
Yes, of course.
Okay. You see at the top where you're doing the what is it called? The confidence interval?
Yeah, yeah.
Okay. I have a
Here,
question. How do we know which the degrees of freedom? Like, do I
okay.
need
As I
N1
said,
or
the degrees
N2?
of freedom here, we use 39, the smaller of the two. How do we know that? If you go
Okay.
back to the original question, the question says they have different variances, okay? When they say different, I will look at the case when we are assuming they don't, okay? By the time we get to the next question, I think your answer is about degrees of freedom and why we are doing this. I guess this one, right?
No,
Fold.
I would just wanted to make sure, like, depending on, I guess with mu sub one and minus mu sub two, if they're in like, they never go in the other direction, right? They never go, what is that, less than? They never go more than, right?
No, they could, but again, I'm not too sure if I follow your question. Let me just go back.
Well, I just wanted to know how like the degrees of freedom
Okay, first of all,
were chosen, but you said it's the
so you're
less of the
okay with
two.
this one, right? I want you to see you're okay with this one, right?
Yeah.
Okay, so we are really following this. It could be, of course, it can go. It may be that we assume mu1 is larger. I mean, of course, the company won't claim that, but if a company claimed, okay, we have, uh, yogurt cups that make more calories, then mu1 is larger than mu2. It
Yeah.
could be, but in
Would
this
it
case, it can't.
change the degrees of freedom, or do you always go with the one
But
that has
okay,
the less?
here's the deal. When you assume different variances,
Mm-hmm.
you choose smaller of the two based on texts.
Okay.
Based on a calculator is a different story. Based on a calculator, again, look at the formula. Based on a calculator, we use this formula, which is the reason they go with that because calculation is pretty involved. You can always calculate it.
Yeah. Okay.
So the degrees of freedom, again, the degrees of freedom, in this case, we are paying attention to the fact that we are saying different variances. We go with smaller of the two if we are doing it by hand.
Okay. Thank you.
But if we are doing it, my pleasure. If we are doing it with the technology, they calculate degrees of freedom for us. Okay. I hope that answers the question.
Yeah. Thank you.
Sure. All right. So again, to emphasize this degrees of freedom is calculated using the formula that I showed you. That's why normally they don't use that with the limitation. So to make some sense out of this, in fact, I'm going to look at the same question and we are going to assume equal variances. In reality, we never do that. Okay, everybody? In reality, we never do that. But just in case, what happens? So I hope you see that the information from the previous question is there, and H0 mu1 equals mu2, H1 mu is less than mu2, claim left tail test. That part is not changing. So what is changing? When we assume equal variances, okay, test statistic has a different formula, everybody. Test statistic has this formula, x1 bar minus x2 bar over the square root of sp squared over n1 plus sp squared over n2. This s sub p, this s sub p has this formula, which is the pooled variances. And I'll show you with the technology as well, which is calculated as such, n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared over n1 minus 1 plus n2 minus 1, the sum of the two degrees of freedom. So therefore, let's put this into this equation after we find S sub p. So S sub p is pretty, you know, tedious to find, but nevertheless very straightforward. Now plug in everything into this formula, and that gives you test statistic, everybody. So we calculate the test statistic. Now here's the interesting part. Alpha is still the same, alpha 0.01, but degrees of freedom is sum of the degrees of freedom, this 88, which means n1 minus 1 plus n2 minus 1, the sum of the degrees of freedom, the sum of the degrees of freedom, everybody. So 50 minus 1, 40 minus 1, add them up, 88. Now, why did I put almost 90? Again, the limitation of a table. If you're using technology, you have 88, you have the answer, you're done. But if you're using a table, it may not have 88. If it has it, use 88. If it doesn't, then the closest number to 88 in the table that you use most likely should be 90. So when we use the table, we end up with this number, negative 2.368. Graphing will help us see. So if you graph this, here's your critical value, negative 2.368. Here's your test statistic, which is smaller than that, right, everybody? So you reject H0 because the test statistic is way into the rejection region. So if you are rejecting H0, let's go back to this one. If you are rejecting H0, what are you not rejecting? H1. So the claim becomes true. If the claim is true, you rewrite the claim. There is sufficient evidence to support the claim that company A's yogurt cups contain on average less calories than that of its competitor. So when we used equal variances, the result was different. And again, normally we don't assume that. We want to calculate the p-value, and I want to show you again with the p-value class. It's the area to the right, to the left of test statistic because it's left tail test. This area, and clearly it's less than alpha from the graph. But if we were to use a table, degrees of freedom, we use 90. Why 90? The table that I'm using doesn't have 88. So this number is between these two numbers. The p-value is between these two numbers. That's the limitation of a table. And clearly the p-value is less than alpha 0.01. Same decision, reject H0. But if we were to use technology. Notice what we are going to do. We are going to use t-sample t-test. The final answer pulled yes. Take a look at what happens. So we put two sample tests, x1 bar S1 N1, x2 bar S2 N2, mu1 less than mu2. Where it says pulled, you say yes. Why? Equal variance. So look at the result. Degrees of freedom is 88. Remember we had it 88? The degrees of freedom is 88. We use 90 because of the limitation of a table, but we did have it, so that's good. And the p-value is 0.0085, and then 3, just 5 doesn't change. Clearly less than alpha of 0.01, same decision. So for equal variances, it worked out the same. Let's continue with the confidence interval for this. We want to make a 98% confidence interval, and I'm going to remind you, whenever we have a one-tail test with alpha of 0.01, another alpha of 0.01, the right tail test makes the 98%, makes it equivalent to 98% confidence interval. If it was a two-tail test, this should be 99%, but this is one-tail test, so this is 98% confidence interval. All values are the same. So x1 bar minus x2 bar plus minus e. Again, we don't have to use too much. I'm going to remind you of all these formulas. Okay, this is the formula that we have used. And for E, T alpha over 2 squared of SP squared over N1 plus SP squared over N2. And if you look at this part, is identical to this part. And I'm going to remind you, in the previous page, we found the numerator to be -3, the denominator to be 1.23376. Why am I using that? Because I want to show you that I'm not going to do the recalculation again, because I'm going to use the information from the previous page. This number is my T from the previous page. This number is this one. So I'm using this two, and I'm using this two. Makes life easier. So there's really not much of a calculation, and I get 2.9216. And even this part, x1 bar minus x2 bar, is this number, -3. So -3 plus minus this number. So mu1 minus mu2 is between the two numbers, -5.9216 and -0.0784. Both of them are negative. Reject the null hypothesis. If one is negative, one is positive, then fail to reject the null hypothesis. So because the confidence interval limits do not contain 0, there is a significant difference between the two means. Reject the null hypothesis. So same decision making. Now, if we were to go with the technology, we're going to use two sample t interval. We end up with the following. x1 bar S1 N1, x2 bar S2 N2, confidence level of 98%. Fold, yes. Look at the numbers. -5.923, well, very close. If I stop at this number, they're identical. -0.766, -0.0784. Again, the difference is due to the fact that we do a lot of decimals with the calculation. Nevertheless, the answers are almost the same. Needless to say, same decision. Same, almost. Tester claimed that weights of male college students have a larger variance than female college students. Use a significance level of 0.05 and assume that the populations are normal. Alpha is 0.05. And here's the information given. For males, N is 31, X bar is 168, S is 28. For females, N is 29, X bar is 125, S is 25. And we are going to use the test statistic S1 squared over S2 squared. We are going to use the F distribution because of the limitation of the F distribution, everybody. We always choose the two groups such that the one with the larger S is the first group. For the sake of argument, if this was given as the second group, you would change it yourself to the first group. Again, F distribution is very limited. You choose the groups so that the one with the larger S value is the first group, always. So given normal distribution, males N131, S1 is 28. We don't need the X bar is given. Females N2 is 29, S2 is 25. So we choose this one to be the first group. Notice the one that is given, it doesn't tell you which one is the first, which one is the second. We choose it in this manner. Now, we are going to write the first step. Now, I want to discuss the first step. Take a look. Sigma 1 squared equals sigma 2 squared because use a significance level and assume the population are normal. So we are testing the variance. If you're testing the variance and you are comparing it to a number, using chi-squared. But if you're comparing two different populations, males versus females, in its F distribution, sigma 1 squared equals sigma 2 squared. We are saying sigma 1 squared is larger than sigma 2 squared, which makes it the right tail test, which makes it a claim. I just want you to pay attention to this one. Okay. Or you may write the ratio of these two is 1 and the ratio of these two is larger than 1. So use this one or this one. Don't mix them up. Or maybe you use sigma 1 is equal to sigma 2. Sigma 1 is larger than sigma 2. Which one do you use? If they are giving you options, you choose the way you like it. If they have picked sigma 1 squared and they want, and this is a blank, you have to use sigma 2 squared. So pay attention to three different ways that you can write it and how you would write. And by the way, for the sake of argument, okay, when sigma, if sigma is given, and then sigma when 1 squared has to square, you have to square that number. So the next one is to calculate the test statistic. It's a very simple process, S1 squared over S2 squared. So 28 squared over 25 squared, 1.2544. Now, the next one is to find the critical value. The choice of alpha is 0.05. It is a right tail test. Now, you need two things. You need degrees of freedom of a numerator, which is the top. N1 is 31, so 31 minus 1. For the bottom, N2, 29 minus 1. So degrees of freedom of a numerator is 30, for the denominator is 29. So when you go to the F table, the F table has various alpha values. Alpha equals 0.01, alpha equals 0.05, alpha equals 0.1. You choose, the very first thing you choose, proper alpha. Alpha is 0.05. Then you have degrees of freedom for the numerator at top, the top row. The degrees of freedom of the denominator is on the left column. Because of the limitation of the room, I just chose for the denominator 28, but there are more than that, everybody. So this is 28. Over here, look for number 30. Put them together, and here's the answer, 1.8687. A graph really helps. So alpha is 0.05. The critical value is F equals 1.8687. The one we have calculated is 1.2544, way into the non-rejection region, failed to reject the null hypothesis. It's way into the non-rejection region. So let's go back to this one. So if you're not rejecting the null, you're rejecting the alternative. You're rejecting the claim. The claim becomes false. And you are rewriting it. There is not sufficient evidence to support the claim that weights of male college students have a larger variance than female college students. If we were to do the technology, two sample F test, that's what we do. And we plug in S1, N1, S2, N2. And we are going to say greater than. Because of the limitation of this table, we want to make this always right tail test. And we want to make sure S1 is larger than S2. We do the calculation and notice what it gives us. It gives us this value that we have done the calculation already. F is 1.2544. This is test statistic. Here's the p-value. The p-value clearly 0.27. Let's say you stop at 4, you change it to 5, right? Because next to it is 5. So 0.275 clearly larger than alpha of 0.05. Same decision. Fail to reject H0. Fail to reject H0. All right. Could somebody read this, please?
Directional asymmetry is a phenomenon whereby in a population, one side of each organism is consistently larger than the other, i.e. left larger than right. An evolutionary biologist studying DA measures the length of the left and right wings of a sample of Drosophila, a type of flies whose members are often called small fruit flies, collected from nature, and she gets these data. A, the researcher decides to perform a two-sample t-test to determine whether the mean wing differs between the left and the right side of these flies. What type of t-test will she do? A equals 0.05 and B, find the 95% confidence interval of the differences between the means.
Excellent. Well, we are dealing with the same group. We are going to look at the left and right. Therefore, we must use paired t-test. Paired t-test. We are going to calculate the difference. So it doesn't matter you say L minus R or R minus L. It really doesn't. You just want the difference. So for example, L minus R, 1.34 minus 1.26 gives you 0.08. We do the same thing for all of them. So for the second one, 1 minus 1.28 is minus 0.28. For the third one, 1.09 minus 1.36 is minus 0.27. So this difference is the left minus the R, L minus R, L minus R. Okay, everybody. So we are going to write L minus R. Okay. So let's see what happens when we have that. If you look, I mean, in short, if you look at the difference and you do the t-test on that, that will give you the result. Now they call it d bar is summation of d over n. You remember x bar is summation of x over n. So we are looking at this column. S was summation of x minus x bar quantity square over n minus 1. Now we're going to say d minus d bar over n minus 1, so on and so forth. Okay. So we put the information, okay, stat edit clear. We're going to clear two lists, L1 and L2. Type in the data, these two in L1 and L2. And then L1 minus L2, we are going to store it in L sub 3 becomes D. Okay. And then we use this information, stat, calc, so on and so forth, to calculate D bar and S sub t. And notice D bar negative 0.0906. We have entered it. It's done the calculation for us. S sub t is here. N is 17. And on purpose, I use lowercase d here, uppercase d. Uppercase d here or lowercase d. It doesn't matter. In some text, they use lowercase d. In some text, they use upper. And I want you to see that it is the same, everybody. Okay, so just in case if you come across. All right. Now let's do the math, and this is the information. We are going to use per t-test. This is the information we got from the previous page we calculated. And here's the test statistic. I hope you remember it was x bar minus mu of x bar s over square root of n. Now we use d bar instead of x bar. So step one, h0 mu sub d, or simply mu. Remember, we would write just mu is equal to 0. Okay, because we are checking to see whether they differ. So mu sub d is not equal to 0. And since we are checking that, we're going to go with the claim. By the way, not equal means two-tail test. So this has got to do with this inequality. And this, you can, in this case, in essence, you can choose. Test statistic, plug in. Again, d bar lowercase, d bar uppercase, on purpose. Mu sub d, mu sub, interchangeable. By the way, sometimes they don't even write that because this will always come from H0, which is 0. So you don't have to. So depend on the text. They may not write this. They may write it. If they write it, it's always 0 because it comes from H0. Remember, H0 as the equality. So plug in all the values, negative 0.09059 over S, which is 0.22829, right? Now, by the way, notice I even put more decimals here because you really want to write the exact, as many decimals as you want in the intermediate steps over the square root of 17 gives you negative 1.636. Critical value comes from the choice of alpha, which is 0.05, degrees of freedom, which is n minus 1, 17 minus 1. And it's a two-tail test, and t becomes plus minus 2.120. Remember, you have to divide this by 2 and put it in each tail. So each tail has a 0.05 divided by 2, or 0.0. Okay? So when you look up the table, it gives you those values. Test statistic negative 1.636 is somewhere here, and it's way into the non-rejection region. So do not reject H0. If you're not rejecting H0, whether you're rejecting H1, the claim, therefore the claim becomes false. If it's false, that means there is not sufficient evidence to support the claim that the mean wing differs between the left and right sides of these flies. Therefore, she cannot conclude that this population possesses DA because the mean lengths of the wings on the left and right side do not differ significantly. Remember, dA refers to directional asymmetry. You can always use a technology, by the way. The technology that you would use is one t-test, okay? T-test, but for one population. So if you use that t-test and you plug in, you can put matched pair t-test, enter mu sub 0 equals 0, list L sub 3, which was L1 minus L2, choose right tail test, left tail test, or two tail test, and calculate. So that's basically what happens. I'm going to leave it for you to try the technology. All right, let's come up with the 95% confidence interval. Let's come up with the 95% confidence interval. As you recall, alpha was 0.05. And we were dealing with the two-tailed test. Alpha was 0.05. We were dealing with the two-tailed test. It corresponds to 95% confidence interval. And we get the same critical value of plus minus 2.120. Okay, because again, degrees of freedom is the same in -1 or 17, -1 or 16. So it's the same as before because alpha of 0.05 corresponds to 95% confidence. All right, so D bar plus minus E. I hope you remember it was X bar plus minus E. And where E was T S over square root of N, now E is T S sub D over square root of N. It's really the same thing in essence. And so plug it in, we have all the values, we have the T, we have the S sub T, we have N, and the calculation will result in 0.1174. And D bar is this number, so subtract this number from it and add to it. So this number, we are going to subtract 0.1174 from it, and we are going to add to it as well. It gives us negative 0.208, less than mu sub d, less than 0.268. So somewhere between negative and positive. So it contains 0, same result. Since 0 is contained in the interval, the decision is to not reject the null hypothesis, H0 mu sub d equals 0. So the same decision that was made, it is also made here. So again, an actual application in biology. So if we were to use the technology, this is what we get. Could somebody read the last question?
And an ecologist is concerned with whether pollution entering part of a preserved area is compromising the health and growth of an endangered species of snake. To determine this, he decides to measure the length of a set of mature adults from the polluted area and an unpolluted area. The researcher decides to perform a two-sample test T, to perform a two-sample t-test to determine whether the mean length of these snakes differs between these two areas. A equals 0.05.
Perfect. So class, we have two sets of data. We are going to assume different variances. you can never assume equal variances unless it's mentioned. If you recall in the beginning, one of the questions we did it both ways. Assumption of different variances, assumption of equal variances. If nothing is given, always different variances. That's the assumption. So what we want to do for this group and this group, we want to find the sample standard deviation, we want to find the mean, we want to find the n. Obviously, the n, so for this group, n sub 1 would be 15. For this group would be 17. Now, as far as the mean, add them up, divide by 15. For this one, add them up, divide by 17. And standard deviation as a formula. You can plug it into a calculator, and the calculator gives you an answer. And notice I put a lot of decimals. So for this group, S1 and X1 bar are calculated. For this group, S2 and X2 bar are calculated. And N1 was 15, N2 was 17. And here's the formula. Everybody remembers the formula. T is X1 bar minus X2 bar over square root of S1 squared over N1 plus S2 squared over N2. So first, mu1 is equal to mu2. That's H0. H1, mu1 is not equal to mu2, which makes it a two-tailed test, and that's the claim. Mu1 is not equal to mu2, that makes it a two-tailed test, and that's the claim. We are going to calculate the test statistic. We have all the information here, we plug in. So X1 bar minus X2 bar, X1 bar minus X2 bar, which is 27.26666 minus 24.647058882, and over the square root of 2.658 quantity squared over 50 plus 2.620 or 2.621 quantity squared over 40. I'm showing you what I can, but I'm using all the possible number of decimals because I don't want to get to round up here. You do the math, you end up with 2.8022. Critical value comes from the choice of alpha, which is 0.05. And we use degrees of freedom as smaller of the two. So 15 minus 1, 17 minus 1, this gives you 14. Again, this is for the limitation of a table class. And this results in plus minus 2.145. Now, if we do the graph is extremely helpful to see what's going on. The graph gives us the two critical values, negative 2.145, positive 2.145. And the test statistic of 2.8 is larger than 2.145. So it's somewhere here, okay? Way into the rejection region inside the right tail. So the decision is to reject H0. If you're rejecting H0, whether you're not rejecting, whether you're accepting H1, so the claim becomes true, and you reiterate and you rewrite, there is enough evidence to support the claim that the mean length of these snakes differs in these areas. It is larger in the unpolluted areas since test statistic is positive. By the way, we claim that they are different, but if this is positive, that means larger. If it's negative, that means smaller. That's another meaning of these calculations. Now, calculator, okay, has a different take on that. Note calculator uses a different degrees of freedom. Remember, we use 14, but degrees of freedom is 20.3930, whatever. And it is calculated using this formula, everybody. So the critical value alpha is 0.05 degrees of freedom. Now, if you want to go with the table, you have to round it to 29. You always round it down, by the way. For degrees of freedom, you round it down. Even if it's 29.7, you go with 29. And so 29, okay, by the way, this test statistic that we calculated here, of course, it's slightly different because it uses, of course, a lot more decimals than we do. Okay, here's the p-value. So critical value alpha is 0.05, degrees of freedom is 29. The critical value, if we go with the table and number 29, we get a critical value. It's not too bad, but it is different than what we have, because over here we use 14. And the larger the degrees of freedom, it's slightly smaller, okay, because it becomes closer to the actual z values and tables. And the p-value, what is the p-value? 0.008. I'm going to change this 8 to 9 because this is 9, which is clearly less than alpha of 0.05. And we get the same decision, reject H0, because actually the critical value here and here were fairly close. We ended up with the same result that we did it by hand versus technology.